Next part in the chapter number 8 is still dedicated to nonlinear modeling, but this time it is dedicated to logarithms, so model with logarithms. When we are using this kind of model, it is very convenient if we have some relationship with elasticity. For example, percentage change of one variable is related to percentage change of other variable. So, for example, in this case, price and demand. Also, if we have some kind of multiplicative relationship, for example, well-known Cobb-Douglas production function, you can transform this function and then to have it in logarithm shape, and then afterwards you can transform it into linear shape and linear form, and then solve it through ordinary least square methods. Also, if we have growth model, some exponential growth, like here on the picture, you already see here that we have independent variable, beta 0 and beta 1, but if we change y into logarithmic form, then we can transform the entire equation in the form of a linear model and then solve it y tilde, and out of that we can have the original values of y. So, just to remind ourselves about the basic rules when it comes to logarithms, we can see here that e is actually constant, and logarithm of y is actually x. So this is very convenient. We have some growth, and then the slope of this curve is actually 1 over x. When it comes to algebra with logarithms, so ln of 1 over x is actually minus ln x. You see how it goes if it is adding, if it is division and subtraction of logarithms. If you have x to the power of a is actually constant. It can be before the logarithm. And the most convenient thing why we want to use logarithms is so that we can express the changes in percentages. So logarithms are actually related to percentages because difference of two logarithms is actually percentual changes in some variable. And we can say that changes in logarithms of our dependent variable is approximately equal to percentage changes of original values of the dependent variable. We will see there is possibility of 3 different logarithmic models. First one is linear log. Actually, types of models are different when it comes to the position of logarithms in our equation. If it is on the right hand side, then you have linear log model. So dependent variable is still linear, but one of the independent variables, or all of them, are in logarithms. Log linear model is the opposite. When you have the logarithm of the dependent variable on the left hand side, but on the right hand side you have linear form. And log if you have logarithms on the both sides. So it doesn't mean that if you have multivariate model with more than one independent variables that all of them need to be logarithmed. No, some of them can be still linear and some of them can be in the shape of logarithm. So it is also possible. Let's go to linear log model. So beta 1 coefficient is related to logarithm of independent variable. What it actually means that 1% of change in x gives us the percentage of change in y, but for value of beta 1 times 0.01. So you need to move the dot for 2 places to the left. For example, in our test course, if we have income as independent variable, that average income in districts are actually influencing the size of test scores in those districts. We have beta 1 36.42. What it actually means that if income goes up by 1%, so our independent variable goes up by 1%, on average, test scores goes up by 0.3642. So we have divided this number with 100 to get the real number of beta 1 for the test scores. Let's go to the example. So we will have test score as dependent variable and logarithm of average income as independent variable. These are all data. Average income is here, test scores are here. You'll go straight to transforming our dependent variable, average income. We need to make logarithms. It is very easy. So if we mark average income and then go here to logs of selected variables, there it goes. This is our new independent variable. Now, ordinal squares, test scores will be dependent. Logarithm of average income will be independent variable. We will make it with the robust standard errors. And this is our model. Now we see that beta 1 is 36.4. So please be reminded that it is actually average change of our dependent variable. In the case of logarithm of average income if average income goes up by 1%. So the changes in test scores will be actually 0.36 test points. So the changes of independent variable is in percentages, but changes of your dependent variable y is in original units of measure. So in this case, in test points. Let's go back to our example. So once more, it is very important. So these are actually test points. If income goes up by 1%, income, independent variable, goes up by 1% because it is under logarithm. Test scores, our original value, will go up by 0.3642 test points. So it is in original units of measure. If we want to see the speed of the change, if we want to evaluate, assess the slope, then we again, because it is a curve, like we did already in the first example with the polynomials, we need to decide about the interval for which we want to calculate the change of y. For example, if income goes from 10 to 11,000, so it actually means that we will put 11 as a value of x and 10 as a value of x also, and subtract one equation from the other. So this will be actually the changes in test scores if income goes up from 10 to 11,000. Also, we will do that on some different part of the original horizontal axis, maybe for the values from 40 to 41,000. So we will now input 41 and 40 in our equation. So you see that changes in y, changes in test scores are much lower for higher average incomes of families, of households. So it is also obvious on the graph that changes from 10 to 11,000, you have the higher slope here, more extreme growth of test scores. But here, from 40 maybe to 50,000, 40 to 41,000, you are getting more horizontal line here. So the increase of test scores is slower for the richer districts in California. When it comes to log linear model, the situation is opposite. Now we have dependent variable under logarithm. On the right hand side, everything is linear. So how do we explain beta 1 now? One unit change in x, so in original units of measure, gives us 100 times beta 1 percentage change in y. So now this is in original units of measure, and this is changed in percentages. So this is one more explanation about this. Let's go to the example. This is not example from the book, but anyway, it is really simple. We are observing that how age in years is influencing the earnings, how much people will earn if they are older or younger. So if age goes up by 1 year, so this is beta 1, if age goes up by 1 year, earnings goes up by 0.96%. So 100 times 0.0096. So age is in original units of measure, 1 year, while earnings, since it is under logarithm, it will be changed in percentages. And the final model is log-log model, but we have logarithm on both sides. It is the easiest model because everything is in percentages. So it is actually an elasticity model in general. Percentual change of x will cause the percentual change of y. For example, in our model with the class size, income will be under logarithm like in the first example, but also test scores will be under logarithms. So beta 1 is 0.0554. It actually means if income goes up by 1%, test score on average will go up by 0.0554%. So you don't move dot for any place to the left or to the right. It stays like it is. Okay. One more example. For test scores, log linear, because we missed it because over there it was with age and income. So if we have log linear model, so in this case, unit measure of income will cause the changes in test scores by 2%, 2.8%. Okay, let's go to our example to do those examples. First, we will do the lesson that you saw. So log linear model. We will make test scores on the log in the following way. So we need to log test scores, add logs of selected variable, and now here it is. You'll go straight to the model. Now test score is not dependent variable, but actually log of test scores, while average income will be actually in original units of measure. So this is log linear model. Okay, and here it is. So if average income goes up by $1,000 per household, test scores on average will go up by 2.8%. This is log linear. Now log-log model. We already have two logs that we need. Model, ordinary least squares. Average income, we will put it out, and log average income is going in. So log here, log there. Okay. And now we see it is 0.05, which means if average income goes up by 1%, on average, we can expect the test scores goes up by 5.5%. So these are the explanations for logistic models. And this is the end of presentation.